Today, we're looking into something really quite revolutionary that's got the cycling world buzzing. Imagine getting a real boost on your bike, almost like an e-bike feels. But, and this is the kicker, no motor, no battery, and you never, ever have to charge it. It's true. This new system uses, well, springs to store and release energy. It completely changes your ride. We're going to unpack this right here. Get ready to rethink how you move. So our mission today is a deep dive into this whole fascinating world of mechanical energy storage. We're focusing on this specific invention for bikes. We'll explore how it actually works, the advantages, the science behind springs themselves, and maybe look ahead a bit. Where could this kind of thing lead?
Exactly. And it's more than just a bicycle wheel. It's really a window into the bigger picture of kinetic energy recovery systems. What's so fascinating, I think, is the elegance of it. Using simple, elastic potential energy to solve problems that, well, modern tech often makes really complicated. We can compare it to other ways we store energy, old and new. And we'll try to understand why springs, these sort of humble devices, are making a bit of a comeback.
Okay, let's get into it. This bike wheel, the super wheel, it sounds almost too good to be true. How does it actually give you that boost without any electronics? What's the clever bit?
It's less a trick and more just, well, smart physics. The super wheel uses a really brilliant mechanical setup with springs inside the wheel. They're positioned mainly near the top and center. And the genius part is how they use your own weight, the rider's weight. As you pedal, your weight presses down, and as the wheel turns, this deforms those springs, compresses them, basically. So they store energy, elastic potential energy. Then, as the wheel keeps turning, that stored energy gets released smoothly, giving you a real push forward. It's a direct conversion. Your weight, your motion, turned right into extra propulsion.
Wow. So it's not just carrying my weight, it's actually turning it into an advantage. Like gravity is helping me pedal.
Precisely. You can think of it like that. It's kind of a closed loop, recycling the energy from your own mass and movement. It's reclaiming that little bit of energy that's usually just lost in how you interact with the bike. And the result, they've shown through testing, is up to 30% more power added to your pedaling. Now, for any cyclist, a 30% boost, that's huge. It's not just a tiny improvement. It makes a real difference, especially on hills or into the wind.
30% is definitely significant. But, okay, practicalities. What are the real benefits for someone just, riding to work or for fun compared to getting a standard e-bike? Weight, maintenance.
Good question. The trade-offs are important. The advantages are pretty compelling for a lot of people. First off, no battery means no recharging. Ever.
Right. No plugging it in, no waiting.
Exactly. No range anxiety. You can ride as far as you want. And no extra cost on your electricity bill. Which kind of makes you think, doesn't it? What does it mean to take electricity completely out of the assisted cycling equation? It really simplifies things.
And no battery must mean, well, it's better for the environment, right?
Yeah.
We hear a lot about lithium mining, recycling issues with e-bike batteries.
Absolutely. That's a major plus. This design completely avoids all those environmental concerns tied to lithium batteries, the mining impact, the disposal problems, the energy used in manufacturing and recycling. None of that applies here. It's just a more sustainable way to get pedal assistance. In a way, it's a return to simpler mechanical solutions, moving away from complex electronics and their resource demands. It rethinks what assist means.
That makes a lot of sense from a green perspective, but how easy is it to actually use? Can I just swap out the wheel on my current bike?
It's designed to be pretty adaptable, yeah. They want lots of people to be able to use it. It comes in the common sizes like 700 cents and 26-inch, and it works with standard gears, up to 9-speed systems. So for many regular bikes, you just take off your old rear wheel and put this one on.
So it turns a standard bike into something that feels boosted.
Exactly. Gives you that assisted feeling without the electrics. There's one key thing to know, though, a technical limitation. Because of how the springs are built in, it's not compatible with disc brakes, only rim brakes.
Ah, okay. That's an important detail. So rim brake bikes only.
Right. It's a trade-off for the purely mechanical system, something you'd need to check on your bike.
Fair enough. For many riders, that might be fine. What about the cost? E-bikes can be, well, pretty expensive. How does this stack up?
That's another big advantage. The super wheel costs around 475 euros.
Okay.
Now, compare that to standard e-bikes. You're usually looking at, 1,200 euros minimum, often 2,000, 3,000, or even more.
Yeah, easily.
So this is significantly cheaper. It makes getting that pedal assist much more accessible. It's a great example of how smart mechanical design can cut costs by ditching the expensive electronic parts. The battery, the motor, the controllers, it opens it up to more people.
It really does sound like a potential game changer. Is the idea protected, like with patents?
Oh, definitely. They've secured strong protection. It's patented in Europe since late 2021. And there's an international patent application, too, covering something like 87 countries. They call it WT-Tech weight-to-energy conversion technology.
WTEC.
Yeah. So that protects the core invention globally. And in specific places, like France, they have exclusive distributors, Cycle Cafe, handling assembly and sales. Shows they're serious about it.
Okay, so the wheel itself is fascinating, but let's maybe dig a bit deeper into the core principle. You mentioned elastic potential energy. How exactly do springs store energy so well?
Right, the fundamentals. Elastic potential energy is basically the energy stored inside something elastic like a spring or rubber band when you deform it, when you stretch it, squash it, twist it away from its relaxed shape.
Like pulling back a bowstring.
Exactly. Perfect example. The archer puts in work, deforms the bow, and that energy is stored in the bow material. Then, when released, it becomes kinetic energy, shooting the arrow. The real magic of springs is their ability to deform quite a lot, store that energy, and then snap back to their original shape almost perfectly, releasing the energy. It's this return action that makes them so useful.
Makes sense. Is there a way to measure that stored energy, a formula perhaps?
Yes, there is. It's described by Hooke's law, which relates the force to the deformation. But the energy stored, the elastic potential energy, EP, is calculated as EP equals 1/2 kx squared. So EP equals 12k by 2.
Okay, K and X, what are those?
K is the spring constant, basically how stiff the spring is. A higher K means a stiffer spring, and X is how far you stretch or compress it from its resting point.
And the X squared part, that means it's not linear.
Exactly, that's crucial. The energy stored increases with the square of the deformation. So stretch it twice as far, you store 4 times the energy. Compress it 3 times as much, you store 9 times the energy. This exponential relationship means springs become really effective energy sponges once you deform them significantly.
That's a key point. Are there different kinds of springs for different jobs?
Oh, absolutely. Engineers use different types depending on the need. You've got compression springs designed to be squeezed in things like suspension coils in a car or the spring in a retractable pen. Then tension springs designed to be stretched like on a trampoline or an old garage door mechanism. They resist being pulled apart.
Okay.
And torsion springs, which store energy when twisted, like in a mousetrap or the balance spring in a mechanical watch. Or the spiral springs sometimes used in general cabars concepts. Each type manages force and stores energy differently, depending on whether you need to push, pull, or twist.
So when designing something like the superwheel springs, which work constantly, cycle after cycle, what do engineers focus on? It can't just be shape.
No, definitely not. There's a huge amount of engineering involved. Several things are critical. The wire diameter is a big one. Thicker wire usually means stronger, can store more energy, but it's also stiffer. Then the coil, pitch the gap between the coils, affects how much it can compress or stretch and how much force it takes. The number of coils also matters. More coils often means a softer spring that can deform more.
And the material itself must be important.
Crucial. High-carbon steel alloys are common, but they might use special composites or alloys for better fatigue life, meaning how many times it can flex before breaking, or resistance to corrosion, or just sheer strength. They also worry about relaxation, which is when a spring under load slowly loses some of its force over time.
So many factors.
Yes, and they all interact. For energy release, the same things matter. How fast, how consistently it releases the energy depends on all these design choices. It's a complex optimization for reliability and performance.
Okay, so the superwheel uses these principles brilliantly, but this idea of recovering kinetic energy, KERS, where else is it used? Why is it such a big deal?
Well, zooming out, KERS is really a response to major global issues, running out of fossil fuels, pollution, climate change. KERS is about capturing energy that's normally just wasted, especially heat from breaking and putting it back to use, making systems more efficient without sacrificing performance.
Making things smarter with the energy we already use, basically.
Precisely. Instead of just turning motion into useless heat when you slow down, KERS stores it and gives it back when you speed up. It's been huge in automotive research for decades. Think of all the stopping and starting in city traffic. Lots of wasted energy there.
So how has KERS usually been done in cars and things? What are the main approaches?
There are broadly 3 main types. First, mechanical KERS, often using flywheels. These are heavy discs spun up really fast to store rotational energy. Brake, spin up the flywheel, accelerate, draw energy back out. Very high power, good for quick bursts.
Like in racing cars.
Exactly. Formula One used them for a while. Second, electrical curves. This is common in hybrids and EVs with regenerative braking. The electric motor acts as a generator when you brake, converting kinetic energy to electricity stored in a battery or supercapacitor. Then it uses that power to help accelerate later.
Okay, that makes sense for electric cars.
And third, hydrostatic gears. Uses hydraulic fluid. Braking pumps fluid into a high-pressure tank, an accumulator. Accelerating releases that fluid to drive a hydraulic motor, helping turn the wheels. Potentially very efficient at capturing braking energy.
They all sound pretty complex, though. Why aren't these systems everywhere, especially in regular cars or simpler things? What holds them back?
That's the key question, isn't it? Practicality and cost. While effective, they all have downsides for mass market use. Hydraulics are heavy, bulky, need lots of space. Electrical curves needs expensive batteries, complex power electronics, controllers. And you lose energy converting it back and forth, mechanical to electrical, electrical back to mechanical.
Right, those conversion losses add up.
They do, and batteries have limits on lifespan, charge discharge rates, and cost. Flywheels also add weight and complexity. So all these traditional systems add significant cost and complexity, making them less suitable for, say, an affordable family car, let alone a bicycle.
Which brings us back to springs. The spring-based approach seems to sidestep a lot of that complexity by staying purely mechanical.
Exactly. That's the core appeal for certain uses. A general spring-based curves, designed to be purely mechanical, avoids those energy conversion losses. Imagine a system where braking engages gears that wind up a spiral spring. Then accelerating uses a clutch to release that spring energy directly back to the drive axle. It keeps the energy mechanical the whole time.
Meaning lower costs, simpler components, maybe more reliable?
That's the goal. Using more straightforward, cost-effective mechanical parts, trying to minimize production costs, installation complexity, running costs, making energy recovery genuinely accessible for more applications, not just high-end ones. Early tests on rigs using spiral springs have shown the concept works. You can recover energy mechanically this way.
We focused on conventional springs, but you hinted at advances. What about futuristic super springs? Are we talking about materials that could really change the game?
Yeah, this is where it gets really exciting. Research, like at MIT, has looked into carbon nanotubes, tiny tubes made of carbon atoms arranged into spring-like structures. These are on a whole different level. Theoretically, pound for pound, they could store as much energy as a lithium-ion battery.
As much as a battery. By weight.
By weight, yes. Potentially over 1,000 times the energy density of steel springs. It's almost unbelievable.
1,000 times? Wow, what would that enable? What kind of applications?
It could genuinely revolutionize things. Unlike batteries, they could release energy incredibly fast or very slowly over years with basically zero leakage. They'd likely be much tougher in extreme conditions, super hot, super cold, high pressure, space, places where batteries really struggle.
So like long-term backup power you could just install and forget.
Potentially, yes. Or for devices needing intense bursts of power. Plus, they could drive things mechanically, directly.
Avoiding those electrical conversion losses again.
Exactly. Think regenerative braking, storing energy in nanotube springs, then releasing it straight back to the wheels. No generator, no motor needed for that loop. Saves energy, saves weight.
What's the catch? Why don't we have these yet?
The big challenge is scaling up, making these tiny nanoscale tubes into large, usable fibers or components without losing those amazing properties. That's a huge engineering hurdle they're still working on.
Are there other advanced spring materials being developed?
Yes. Another fascinating area is mechanical metamaterials. These aren't found in nature. They're engineered structures. Researchers, like at Karlsruhe Institute of Technology, have designed materials with specific internal architectures, like tiny interconnected rods. Their innovation uses twisting motions within the structure rather than simple bending.
And why is twisting better?
It helps distribute stress much more effectively. This means the material can deform a lot more, store much more elastic energy before it fails or permanently bends. They talk about theoretical energy density enthalpy being potentially tens or even over 100 times higher than other advanced materials.
So super strong, super stretchy, stores tons of energy without breaking.
Pretty much. That opens doors for more agile robots, more efficient machines, maybe even replacing traditional hinges with flexible joints made from this material. It's about designing energy storage and resilience right into the material structure itself. Very efficient, potentially very sustainable.
Okay, with all this potential, from the simple superwheel to these futuristic concepts, why aren't springs everywhere for energy storage? If they're so great, why rely so much on batteries, especially for big applications like homes or the grid?
It comes down to a few hard realities. The biggest one for traditional springs is energy density, especially by volume. We talked about the superwheel being great, but for large scale. Let's compare it to, say, a Tesla Powerwall home battery. Stores about 13.5 kilowatt hours.
Right, a decent amount for a home.
Its energy density is roughly 100 kilowatt hours per cubic meter. Now, to store that same 13.5 kilowatt hours using steel springs, you'd need a massive volume, around 45 cubic meters.
45 cubic meters, that's like the size of a garage.
Exactly. A single car garage filled with springs, just to match one Powerwall. It's just not practical for bulk storage where space matters.
So a spring system the size of a Powerwall would hold hardly any energy.
Almost nothing useful for a house, yeah.
Yeah.
Maybe 0.04 kilowatt hours in that same small volume. Enough to run an LED light for a bit, that's about it. Even the advanced carbon nanotube springs, while amazing by weight, still lag behind batteries significantly when you consider volume. So for packing a lot of energy into a small space, batteries still win for now.
Are there other downsides? Safety, maybe.
Yes, safety is a real concern, especially with large amounts of stored mechanical energy. A sudden, uncontrolled release from a big spring system could be incredibly dangerous.
Like a giant mousetrap going off?
Kind of, yeah. The massive forces, flying parts. It's a different kind of hazard than, say, a battery fire, which is also dangerous, but perhaps more containable in some ways than explosive mechanical failure.
And what about efficiency if you are converting from electricity?
That's the other hurdle for grid-type applications. If you use electricity to wind the spring, then later unwind the spring to generate electricity.
Yeah.
You lose energy in both conversions.
Right, motor inefficiency, generator inefficiency.
Exactly. Friction, heat. Those losses add up. It can be less efficient overall than just charging and discharging a battery electrochemically. So springs shine when you capture mechanical energy and release it mechanically, like the bike wheel. But integrating them into electrical systems adds efficiency challenges. That's why sometimes things like supercapacitors are preferred for quick electrical energy storage in KERS, despite lower overall capacity.
What a fascinating journey. From a clever bike wheel using basic physics all the way to nanoscale materials and the hard limits of energy density. It really shows how mechanical solutions are still incredibly relevant, even making a comeback.
It really does. It's proof that revisiting fundamental principles combined with material science can unlock amazing things. The superwheel is such a neat example. Efficient, sustainable, smart mechanics. It makes you wonder, doesn't it? Where else could we apply this kind of elegant mechanical thinking to solve problems sustainably instead of just throwing more complex electronics at everything?
So maybe next time you're riding your bike or even just winding a watch, think about it. What other everyday movements, what other wasted energy could we harness with a bit of mechanical ingenuity? The potential seems to be hiding in plain sight. Thank you for joining us on this deep dive. If you enjoyed exploring this world of mechanical energy recovery, please do tell a friend about Le Podcast de Philippe. We're trying to hit 1,000 subscribers. We're really close. Your support helps us keep bringing these stories of innovation to you. Help us get there. Thanks for listening.